Welcome to the Beer Taster's Notebook, the show dedicated to learning about beer. I'm Jonathan Thompson, advanced cicerone, beer judge, home brewer, and beer writer. Welcome back to the Beer Taster's Notebook, episode 7, all about fusel alcohols. So as noted, we're going to explore the different aroma compounds found in beer, breaking them down one at a time. And for the ease of navigation, we'll do one compound per episode. That way it's just easier to reference. And if you didn't care about something, you could just skip ahead instead of trying to figure out where to go within the episode. So we're going to start off with the yeast-derived flavors and aromas. The most common, as mentioned before, being fusel alcohols, esters, phenols, and to a degree thiols. So fusel alcohols is what we're going to talk about today, obviously, and they're the building blocks of esters. So it's a good place to probably start. So they're also referred to as higher alcohols because they're higher in weight. So ethanol has 2 carbons, whereas the fusels have, obviously more than 2. So 1 propanol has 3 carbons. It's kind of a sharp aroma. Isobutanol has 4 carbons and can be kind of solventy. 2-methyl-1-butanol, also called amyl alcohol, contains 5 carbons, and it's pretty harsh tasting. 3-methyl-1-butanol is also known as isoamyl alcohol, which should be pretty familiar to everyone. It's a bit spirit-like, for lack of a better descriptor, kind of mildly sweet, and it's the precursor to isoamyl acetate, which is that banana-like ester found in Weissbier. 2-phenyl ethanol has 8 carbons, and it's got kind of a rose petal, honey-like quality to it. And then methane thiol, which contains 5 carbons, it kind of smells like cabbage. Just to be clear, the number of carbons doesn't necessarily determine what the actual compound is. That it's the backbone, so there could be other side chains or functional groups that are going to contribute to what the compound is specifically. In other words, as we mentioned, like 2-methyl-1-butanol has 5 carbons, as does methane thiol, but of course they're totally different things. So the yeast produce fusels via 2 major pathways. The Ehrlich pathway, which is the catabolism of amino acids, and the major pathway, and then the de novo, which is from carbohydrates. And when the yeast can't get enough inputs from the wort, they start making their own from pyruvate and other glycolytic intermediates. And this often occurs in conditions of low fan, which we discussed in episode 5, if you need to refer to that, higher yeast growth situations, limited oxygen, or elevated temperature. And we'll get a bit deeper into these metabolic processes a bit later in the episode. So what determines fusel production? Well, pretty much everything. Higher temperature fermentation means a faster amino acid catabolism, which means more fusel alcohols. More yeast growth when fan is high, oxygen is high, or gravity is high means more fusels. Low fan means that yeast need to synthesize their own amino acids and therefore more fusels. High fan can lead to more Ehrlich pathway activity and more fusels. Underpitching means more fusels from higher growth. So lots of food and not enough dinner guests, so to speak. So they kind of overeat. And then obviously there's going to be increased metabolic byproducts there. Overpitching might seem then like the obvious solution. And while it can lead to lower fusel production, it can also lead to nutrient deficiency, which then triggers a host of other potential issues. Another thing that can keep fusels under control a little bit is fermentation pressure. So yeast genetics matter a lot here too. And if you're a home brewer or any brewer really, you know that you don't make a Belgian style beer, or at least you probably don't intend to make a Belgian style beer like a double or a triple with clean American ale yeast or a lager strain. You want a very specific Belgian, probably Abbey strain, but at least you want a Belgian ale strain that's gonna create a bunch of secondary metabolites that are necessary for that particular style of beer. Types of sugar matter as well. So glucose, which is obviously the easiest to digest, it will trigger a process called glucose repression within the yeast. So this suppresses the amino acid transferase enzymes, ATF1 and 2, within the Ehrlich pathway. And this suppression promotes faster and more efficient glycolysis that contributes to less overflow into the fusel alcohol production by lower amino acid breakdown. Maltose and maltotriose, which are the dominant sugars, the dominant sugar fractions rather in wort, they will increase fusel production. And because this uptake is going to be slower, so that's going to slow down NADH turnover, which pushes out more aldehydes and therefore more fusel alcohols. This mild nitrogen stress will also trigger amino acid catabolism, And then non-glucose conditions can increase BAT1 and 2, which are the branched chain amino acid transferase enzymes, and that results in the uptake of more branched chain amino acids. Fructose is, as another sugar, is inefficiently transported, and therefore it can cause redox imbalances, increasing more stress. This forces more aldehyde production and reduction, and therefore more fusel alcohols. The thing with fructose is it's a little bit academic in the case of beer because it's not really an issue, but it is definitely an issue in other substances. Sucrose can become rather tricky. So sucrose is a glucose molecule attached to a fructose molecule, and so it needs to be inverted, in other words, split via hydrolysis. So if the invertase, which is the enzyme that does that splitting, invertase activity is high, it's a rapid inversion and glucose is released quickly, and so we get fewer fusels. But if the yeast gets stressed and then invertase gets dialed down, and then we end up with more sucrose in the mix, this causes more stress and then changes the fermentation kinetics. So invertase, as an aside, is used in confectionery and baking. Invert sugar resists the same crystallization that sucrose on its own would, and so the enzyme is used to create liquid fillings and such things. So if you ever have like a candy that's got like a liquid sugar center, probably invertase is the enzyme they've introduced exogenously to invert that sugar and to keep it in a liquid form. That's just a little tidbit there for you. So just moving on, lactose, another sugar less commonly found naturally in wort, but it's added in. So it is unfermentable by yeast, which is why we add it to things like milk stouts and whatnot to give it that creamy feel. But it can cause some osmotic stress. The effects do tend to be minimal at best, though. So that's the basic overview. Fusel alcohols are created by yeast in certain conditions. And now let's get a bit deeper. My goal with this podcast is to make it the most useful podcast possible for students of beer, especially those studying for things like the Cicerone exams. So the idea that I have is to sort of do a general overview of the subject and then go deep into the rabbit hole, as deep as I feel that you as the audience might be tolerant of. Left to my own devices, I could tunnel to the center of the earth, and then we'd have 19-hour episodes that are just probably super boring for everyone except me, and maybe even me. Anyways, I think that makes sense. So let's dive in. And let's start with the Ehrlich pathway. So it was named after Felix Ehrlich, who was a German biochemist who postulated it in the early 1900s. And recalling that the macro view here is that amino acids are catabolized into keto acids and then decarboxylized into aldehydes and then reduced to an alcohol. All right, so here we go. Step one. So the yeast needs the amino acids, and so they pull them into the cells via the transporters. GAP1, general amino acid permease, basically works on all of them indiscriminately. BAP1 and 2 work on the branched chain amino acids, and TAT1 and 2 on the aromatics. There are other permeases as well, but we don't need to really dive right into those. We covered a lot of those in FAN. But which permeases are active is really dependent on FAN levels and composition. NCR, and to a degree, are strain dependent. And once again, all this covered in episode 5. Step 2 is transamination. And this means that an amino group is transferred from an amino acid to an alpha keto acid. So keto acids, by the way, are metabolic intermediates. So these reactions are facilitated by transferase enzymes like ARO8, 9, and BAT1 and 2. This part gets a little bit wacky, by the way, because the amino acid converts into an alpha keto acid and the alpha keto acid converts into amino acid. So I'm going to use an example to make it just a little more clear. So leucine, which is a branched chain amino acid and very key to cell health. So we'll just use that one. So once in the cell, so it's been transported in, the leucine has an amino group transferred to the keto acid alpha keto glutarate, and this forms alpha keto isocaproate, and then glutamate as the other end product. So we've got two end products that come out of that. So we've now got an alpha keto acid, and then glutamate, which we're going to use for building up cell walls and such things. Hopefully that's pretty clear. Maybe I'll put a pathway on the website so it's just easier to visualize. Okay, so step 3 is decarboxylation. And so decarboxylation is the removal of a carboxyl group, which releases a carbon dioxide molecule. And so via decarboxylase enzymes PDC1, 5, and 6, or AOR10, the alpha keto acids lose that said carboxyl group, and this becomes an aldehyde. Sticking with our leucine example, the alpha keto isocaproate becomes isoamyl aldehyde. Step 4 is the reduction stage. And so the aldehyde is reduced to an alcohol via ASH1 and 5. These are alcohol dehydrogenase enzymes, or SFA1. Reduction means, by the way, that a hydrogen was added. So alcohol dehydrogenase is the same enzyme that breaks down alcohol in the body into aldehydes, which is just sort of step 1 in detoxing from ingesting an alcoholic beverage. And so many enzymes are actually bidirectional, and so alcohol dehydrogenase is one of those. So it can pull a hydrogen from an alcohol to form an aldehyde, or it can add a hydrogen to an aldehyde to form an alcohol. The reaction uses NADH as the donor, and then oxidates it to NAD+. So let's run through some more examples just for sport. So leucine is transaminated to alpha keto isocaproate, which is decarboxylized to isoamyl aldehyde and then reduced to isoamyl alcohol. Valine is transaminated to alpha keto isovalerate and then is decarboxylized to isobutyl aldehyde and then is reduced to isobutanol. Isoleucine is transaminated to alpha keto beta methyl valerate and then decarboxylized to 2-methyl-butyraldehyde and then reduced to 2-methyl-1-butanol, aka active amyl alcohol. Phenylalanine is transaminated to phenylpyruvate and then decarboxylized to phenylacetaldehyde, and then reduced to 2-phenylethanol. There are, of course, more, but that might be more suited for print. I'm sure that was as boring for you as it was exciting for me. I'll put out a fusel and ester pathway map once we finished esters in a couple weeks. And then just a couple yeast notes as well. So isoamyl alcohol is higher in Weissbier. And then, of course, the yeast strain favors this production under the right conditions. So, I mean, that strain is turned on for that fusel. Kveik strains tend to be higher across the board. Lager strains in American ales tend to be fairly clean. And Belgian ale strains tend to favor throwing off a lot of phenylethanol, and tryptophan, and tyrosol, as well as a bunch of others. But those are three main ones that they tend to really kick off. So we kind of alluded to this in the beginning, but here are the main fusel alcohols found in beer, along with sort of their thresholds. So isoamyl alcohol is that fruity, malty, or sweet, spirit-like. It can be very solventy at high levels, and its threshold is around 70 to 100 milligrams per liter. Isobutanol has a wine-like sharpness or harshness. And of course, these get worse as they get higher, right? So, I mean, the small amounts can be very pleasant in beers, and then higher amounts can start to, pull us into sort of naphtha gasoline territory. So for isobutanol, 100 to 150 milligrams per liter is the threshold. This is detection sensory threshold, of course. Active amyl alcohol is sharp, kind of like isoamyl, but just more aggressive. 70 to 90 milligrams per liter is the threshold there. 1-propanol is 800 to 900 milligrams, so fairly high threshold. 2-phenylethanol, which is that floral honey-like aroma and key in Belgian ales, has a very low threshold, actually at 10 to 14 milligrams per liter. Methanethiol, as we discussed, is sort of vegetal like cabbage. It's 0.1 to 1 milligram per liter, so very low. Tryptophan, which is a wine-like floral aroma. It's also very common in certain Belgian beers or beers that are brewed with Kveik strain or fermented, I should say. 40 to 60 milligrams per liter is the threshold there. And then tyrosol, which is that floral sweet aroma. You're looking 40 to 60 milligrams per liter there. And so that's probably all we need to talk about as far as fusel alcohols go, because we're going to sort of slide into how they convert into esters in the next episode. So until then, stay thirsty and stay curious.